We're very happy today to have Hirohisa Tanaka from the SLAC SLAC National Laboratory um, to present the colloquium today. Hiro's career has been geographically varied. He got his PhD from Stanford University in 2002, working on the Babar experiment at what was then the Stanford Linear Accelerator Center. He collaborated with several of our faculty here, including Bill Ford and Jim Smith and Uriel Nauenberg on that, and Steve Wagner, who was not then our faculty member, but is now. Then in 2002, he moved to Princeton University, where he took a postdoc on the mini-moon experiment, switching fields to neutrino physics. He worked there for 4 years, and then 2006 took a faculty position with Canada's Institute for Particle Physics, where he was hosted for 9 years at the University of British Columbia, and then 3 years at the University of Toronto. And then in 2018, he moved back to what is now the SLAC National Laboratory, where he is working on the Dune experiment, among other things. So, Hiro.
Well, thank you very much. It's really a pleasure to be here, and thanks for coming out. And just before I get started, some people are asking me about advice. If you're giving a talk longer than 30 minutes, make sure you have some water. This is a lesson that I often forget, and sometimes, usually 25 minutes into the talk, I find myself in an uncomfortable situation. So today I'd like to talk to you about neutrinos, and just to give you a sense of what I'd like to talk to you about. I'd like to start by talking about what is a neutrino and why is it an interesting thing to study, and what else do we need to want to learn about this thing, and why is it challenging. And so the goal is to get a sense of the scientific opportunities we have going forward studying neutrino. And then I would say some of the, not just technical challenges, but I would say some intellectual challenges that we have in continuing our study of the neutrinos, new methods and challenges. And one thing I really want to highlight is that people here at Boulder have really influenced some the way these experiments work and new ideas. And so I'd like to highlight those things, hopefully without getting too technical. Okay? So to start, I just want to take a little bit of a detour and talk about a chair, okay? And let's just say I tell you I have a chair, and you know that's a rather mundane thing, and I tell you something else mundane about it, that it doesn't have arms, okay? But furthermore, I tell you it doesn't have a back, and it doesn't have a leg. And you know, some of these things you can understand that a chair doesn't necessarily have arms, a stool doesn't have a back, maybe a cushion on the ground doesn't have legs, but let's say it doesn't have a seat. But I still insist to you that I have a chair, okay? So at that point, or right now, you're saying, is this some kind of weird attempt at humor, which is failing? Or we could be a little bit philosophical about it and say, well, is there really anything to talk about here? What defines a chair? Maybe as long as the person can sit down, there's a chair, even if there's nothing there, right? Is it something defined by its function? And more importantly, why are we talking about chairs? So this, I thought it came from this novel that I read, 20 years ago or so. I reread this novel about 3 or 4 times. I actually don't find this, so I'm not exactly sure where this came from. But if anyone knows, please let me know. So let's stop talking about chairs, and let's talk a little bit about particle physics or nuclear physics in its early days. So this is a rather exciting time in the 30s. Quantum mechanics was coming together. We understood things like special relativity and general relativity, and then we were trying to get into the understanding of atoms and nuclei. And so there's a process that we know called beta decay, right? And so at that time, people like Hahn and Meitner and others were studying various nuclear processes. And so the hypothesis was that, well, there's clearly a nucleus, there's an electron coming out, there's presumably a remnant nucleus that's recoiling. And probably from your two-body kinematics, you know that based on the mass difference here and energy and momentum conservation, you would expect that electron to come out with a fixed energy every time if you knew what the nucleus was and the daughter nucleus was. But as it turns out, that's not the case. And so this is one of the early measurements of the spectrum. And it turns out that it kind of has this shape which goes all the way up to the endpoint where is the actual energy you would expect if there were a two-body decay. There was another thing that was kind of perplexing, which was the study of various nuclei like nitrogen. And so the picture that came about from this was that, well, clearly that the nucleus of the nitrogen has +7 charge, but somehow it weighs 14 atomic mass units, so approximately 14 times the mass of the proton. And so the hypothesis back then was that, well, maybe there's an additional 7 protons shoved in there along with 7 electrons, because that's those are the only things we knew about. And altogether, basically we can reproduce these properties. It has +7 positive charge, it has 14 AMU. But now the problem here is that you probably recall from your spin addition in quantum mechanics, if you have a system of spin 1/2 particles and you started adding their angular momentum, well, in this case, we have an odd number of spin 1/2 particles shoved into the nucleus, right? And well, if you have an odd number of such things, then the total sum, angular momentum, should be half integer, right? So 1/2, 3/2, whatever. But as it turns out, it actually has an integer spin. And so somehow this wasn't working either. And this sort of caused what we call the spin statistics crisis. So yeah, so what's the deal here? And so if we come back to the chair, some combination of these two gentlemen, primarily Wolfgang Pauli, said, well, let's suppose I have a spin 1/2 particle, but it doesn't have electric charge, okay? And it might not have any mass. And furthermore, its interaction might be so feeble that we'll never see it directly, okay? And so I think the scientific reaction then, or even Pauli to himself trying to justify why he was predicting this, is this some kind of attempt at humor? Is there really anything to talk about at all about a particle that basically doesn't have any properties or doesn't allow it to be detected? And yeah, what does it mean to have a particle that just is kind of there but can't be detected? And why should we talk about such a thing at all? And the answer, as you probably know historically, is that, together these two gentlemen basically say we can solve the aforementioned problems about beta decay. So if we understand that beta decay is not just a 2-body decay, but a 3-body decay where additional particle, which we now call the neutrino or the antineutrino, gets emitted, then that breaks this, allows us to have this continuous spectrum. And then separately, with the spin statistics problem, if we also now say that within the nucleus, there's not just protons and electrons, but actually a spin 1/2 particle that's electrically neutral called the neutron, then we also can solve the spin statistics problem. And I think, Pauli himself, he really struggled with this. Is this really enough justification to really talk about something that seems so hypothetical and elusive? But as we know today, despite that, the neutrino actually does exist. And as we saw, it is fundamental in basically giving us a consistent picture, taking together quantum mechanics and energy momentum conservation and all that, about how nuclei decay. It's a fundamental constituent of the universe, like the electron or quarks. It is it's a basic building block of the universe. It's a critical element in understanding what other particles do and relative to the fundamental interactions, which I'll talk about a little bit more. And it's also an extremely abundant and just omnipresent thing, much like light. It's actually the second most abundant particle after photons in the universe. And despite that, we only even could hypothesize about their existence about a century ago. And then because of that and some other properties, despite its rather elusiveness, its sheer numbers and some of its basic properties, it really plays an essential role in evolving the universe from the Big Bang to where it is today, and things like how the suns burn and explode. And as a research topic, I would say that it continues to perplex us as we learn more and more about it. Okay? So let's talk a little bit more about what a neutrino is. So I hope you have seen the standard model. Just to give you a quick tour around the thing, there are these things called force carriers, which mediate things like the strong interaction, the weak interaction, the electromagnetic interaction. And so as you probably know, gravity is one thing which is not within the purview of standard model, and so it is sort of outside its scope. We have these things which sometimes, we call them fermions, but here we call them matter particles. And so these are spin 1/2 particles that basically come in two types. There are ones that have color and therefore interact via the strong interaction. And then there are these ones that don't have color and therefore do not interact via the strong interactions. And then finally, there is this thing called the Higgs particle, a spin 0 particle, whose interesting properties basically impart mass to the standard model, all these other particles. Okay, and so in a modern language, so just to take you some jargon, so we say that the neutrino is a fundamental spin 1/2 particle. So it's kind of this fundamental constituent. It carries intrinsic angular momentum separate from its motion, like orbital angular momentum, and obeys Fermi Dirac statistics. And it's neutral in two ways. It was kind of, when I was preparing this talk, I was noticing like these little splotches here, and I was wondering what that was about. But what's interesting here is that what it basically is saying is that you can sort of see this splotch which is tied to the gluon. So these quarks, because they carry the charge of the strong interaction, which we call color, they can interact via the gluon. Likewise, these other parts, well, let's go to the electromagnetic force. You can see this blob that kind of goes around like that. These particles have electric charge, so they can therefore also couple to the photon and participate directly in the electromagnetic interaction. And then finally, you see this thing, here's the W. This thing actually goes through all of these quarks and leptons over here. And basically that's saying that the weak interaction actually does participate, does actually interact with all of those spin 1/2 particles. And what you see is that the neutrinos, having neither color nor electric charge, basically that's all that's left for them to interact with. And so they're neutral in two ways, according to the three interactions. They're electrically neutral. They don't have color, so they do not participate in the strong interaction. But they form what we call a chiral weak isospin doublet. And that's just a fancy way of saying that if we have a left-handed neutrino participates in a weak interaction that is fundamentally tied to another particle, in this case, either an electron, a muon, or a tau, the charged leptons. And then the right-handed particle likewise interacts with their corresponding antiparticles, the positron, the mu plus, and the tau plus. And so we can sort of define these kind of interaction Feynman diagrams which show how they interact. If electron muon, for example, when it interacts, will produce an electron. Muon, neutrino produces a muon, and so on and so forth. And so basically all this is almost enough to specify exactly how the neutrino is supposed to behave according to our understanding of the standard model once you stuff it in with the rest of the quantum field theory. That being said, there is one thing, one more thing, or should I say, a category of things that we need to specify, which is that we saw that the neutrinos interact via the weak interactions to produce these charged leptons. And so we're defining three species, or sometimes we call flavors of neutrinos, likewise by their antineutrinos. But what we discovered about 30 years ago is that the neutrinos also have mass. And so there's another way in which a quantum number, basically, in which we can define a neutrino, which is by their mass. So there's a neutrino with a mass m1, m2, and m3. And furthermore, what we see is sort of a very classical quantum mechanical, a ubiquitous quantum mechanical system where you have two observables. Those eigenstates don't correspond to each other. And so basically, what we call a flavor eigenstate is, in fact, a linear combination through the superposition of these mass eigenstates. And basically, all these other things are orthogonal linear combinations of those three states. Okay? And then basically, there's a unitary transformation, which we call U, which basically takes us from one basis of this quantum system to the other, to the mass states to the flavor states. So what's a bit perplexing, so far it's relatively straightforward, but I think there are a number of things which are perplexing about this. You might have learned from your particle physics class that the standard model really doesn't like particles having mass. And so we have to basically have this backdoor involving the Higgs boson and the Higgs mechanism where we sort of sneak in the mass term and give the particles mass. And so basically all the particles, the quarks, the leptons, and the massive gauge bosons, you could get their mass through their coupling with the Higgs boson. But one thing that's really mysterious here is that if we look at the spectrum of masses, right? So this is sort of mass going upwards on a logarithmic scale, and we have our quarks here. That's probably the up-down charms, strange charm, bottom and top. Here are charged leptons. Here are bosons. The neutrino is at least something like 1,000,000 times more lighter than the lightest next known particle, which is the electron. And so that really begs the question: does neutrinos do neutrinos get the same way, mass the same way as all these other standard model particles, or is there something else? Is this some kind of clue that a different mechanism is at play in terms of its mass? There is another thing about this. Well, I mean, in order to complete the picture, we also need to know what these masses are, in particular the mass splitting. We also need to know, basically what I'm showing you here are mass splittings, but then we also want to know what the scale of the neutrino masses are. And then finally, we want to know basically what are these linear combinations? When we look at something like the third mass eigenstate in the neutrino, how much of each flavor is there in there, and likewise M2 and M1. And so there's a whole bunch of interesting questions here. And one very direct question is that when you have a 3x3 system like this, it allows for the mixing to actually have an irreducible complex phase. And that phase comes back in some phenomena that I'll mention where the neutrinos and antineutrinos actually behave differently. And is a manifestation of what we call charge parity symmetry violation. Basically, an imbalance between how a matter system and its corresponding antimatter system behave. Another thing, these colors are actually indicative of what we understand the flavor contents of these masses to be. And another big picture thing you might notice here is that there's like basically all this random color all over the place, which is showing that there's a very, very strong mixing. There's a very little correspondence between the flavor and the mass eigenstates, and they're kind of maximally mixed up. And so that's another mystery. Is there a pattern here or something that would explain why that mixing is so strong? And so there are sort of questions that people are sort of probing around and trying to, we don't really have any definitive answers to, or even really what the definitive question is. But one way to say this is, well, first of all, as we saw, because the neutrino masses are small, do they have an origin that's different from other standard model particles? Why is this mixing so large? And is there some kind of relationship between these two things? And there are people who have some theories and ideas about how those things can be connected. So I'd like to talk specifically about a neutrino phenomenon that allows us to probe some of these particles. And this is what we call neutrino oscillations. And this is also, once again, sort of a ubiquitous quantum mechanical phenomenon or representation of a ubiquitous quantum mechanical phenomenon that occurs when you have some kind of a observable which is not an energy eigenstate. And so if you prepare an eigenstate of that observable, in this case the flavor, then that observable will precess with time because it's not an energy eigenstate, right? And that's exactly what happens here. We can produce a neutrino through the weak interaction in a certain flavor, but because that flavor state is not an energy eigenstate, the flavor will precess, and at some time later, it will have some chance of being detected in a different flavor eigenstate. And that's what we call the neutrino oscillations. And basically, this is the formula for this. The probability that you produce a neutrino in flavor alpha, electron mu or tau, and detect it later in flavor beta is this complicated formula. But the main part is that there are these oscillations, right, that are a function of the distance that the neutrino travels divided by its energy. It's effectively the proper time between the production and the detection of neutrino, whose frequency is determined by the mass splittings. And so the bigger the mass splitting, the faster that precession happens. And then the amplitudes are governed by these U things. And the U is basically that mixing matrix that we just talked about that relate the flavor and the mass states. Okay? And so by measuring this probability, and in particular as a function of L over E, we can actually start to probe these fundamental properties of the neutrino, the mass splittings, and these mixing or mixing matrix elements. Okay? There's another part here. So yeah, this kind of weird symbol that looks like an R stands for the real part, and that thing that looks more like an F to me, but is actually an I, is the imaginary part. And so when you talk about neutrinos versus antineutrino oscillations, this part actually switches sign, okay? And that can actually result in the probability for this kind of transition happening in neutrinos to be different from the corresponding transition in the antineutrinos. And this is basically how we could detect CP violation of this form that I discussed before. Okay, so I'd like to talk about a particular form of oscillation, which is producing muon neutrinos and looking for electron neutrinos later. And right now, for various reasons, this is really the best hope we have for studying explicitly a flavor transition, where we start with one and explicitly observe neutrino different flavor. And so if we go over here, right, this is sort of a representation of the masses that we know, and then a particular complex phase that can be present within this mixing, describing how much of these things are in there. And one thing I didn't mention before is that based on our information, the neutrino oscillations are telling us primarily about the differences or the splitting between the mass eigenstates. And as a result of that, we actually have an ambiguity right now in terms of, well, we know that there's kind of a slow oscillation that's driven by this splitting here. And then this big splitting is also driving a faster oscillation. But as it turns out, with the data we have now, we can have two different configurations of this. One of this called the normal hierarchy or ordering, and this thing called the inverted ordering, where the small splitting is on top. Okay? And as it turns out, this channel here, nu mu to nu e, when you actually propagate neutrinos through matter, can tell us, can give us some indication about whether we have normal or hierarchy and inverted hierarchy. Furthermore, this channel is also sensitive to basically how much of this third mass eigenstate is actually muon neutrino, and that's a parameter which we call related to what we call theta 2,3. And so there are all sorts of properties in the neutrinos that are sort of embedded in here. And just to give you a rough idea of what we're looking for, well, so first of all, we have this thing called the complex phase of the neutrino. And so that's related to that imaginary term that we discussed. And so that relates to, so we have sort of this continuous modulation between, anti-correlation between neutrino versus the anti-neutrino oscillations of this channel. So if you crank delta CP to minus pi over 2, it actually enhances the neutrino channel, suppresses the anti-neutrino channel. You go to pi over 2, it goes the other way. At 0 and pi, they're actually the same. Now, with the mass ordering, because of this matter effect, there's actually kind of this binary switch, where if we had the normal hierarchy, the matter effects enhance the neutrino mode of this oscillation, but suppress the anti-neutrino mode. And so nu mu to nu e is high, nu mu bar to nu e bar is low. And likewise, if it's inverted hierarchy, it's the other way. And so it's kind of like the CP violation, but this is a discrete parameter, basically one way or the other, as opposed to a continuous parameter. And then finally, we have this thing called the theta 2,3 octant, which is what I would call a common mode parameter. The bigger theta 2,3 is, the bigger both nu mu and nu e are. So we kind of have like this three things going on here. And so we have to sort of disentangle this by looking at the neutrino modes of this oscillation, the anti-neutrino mode of this oscillation, using the spectrum information, and then basically seeing these matter effects depend on how far the neutrinos go. And then we can also use other neutrino oscillation channels to constrain some of the parameters. And so somehow we have to put this all together and disentangle all these parameters. Okay? So I'd like to talk now a little bit about the technical challenges in studying neutrinos. So we're going to study neutrino oscillations. How do we do it, and what makes it so hard? So as you probably know, most particle detection methods are based on some kind of electromagnetic interaction. It could be ionization or scintillation. It could create radiation. But as we discussed, a neutrino is electrically neutral. And so we can't really directly observe the neutrino via those means. And so what we basically have to do is wait for the neutrino to induce an interaction on something, usually a nucleus standing around somewhere, via the weak interaction. And that emits particles that tell us what the properties of that neutrino are. And so typically we can write the reaction as, well, let's say an electron neutrino interacts with some nucleus. Because it's an electron neutrino, an electron comes out, and other stuff comes out. And so A is the target nucleus, usually part of our detector. E is what we call the primary lepton, which tells us that we had an electron neutrino. You have a muon, then it's a muon neutrino, right? And likewise, if we had a positron, that would indicate it's an electron antineutrino. The X is basically just a catch-all for everything else that comes out. There could be a revenant nucleus. There could be, protons and neutrons, which are ejected from that nucleus. There could be pions and mesons and other stuff. So basically, all that is what we call X. And one of the challenges here is that we want to study neutrinos oscillation as a function of the energy. And so we have to use sort of energy momentum conservation to basically add up all this energy and infer back the energy of the incident neutrino, and then get its flavor from the primary lepton. So the challenge, as you probably know, is that the chance that a neutrino interacts, at least in the energies that we produce, is very, very low. And so at some point, these gentlemen here actually wrote in the paper that these cross sections, basically the intrinsic measure of how often these things interact, is so small that basically we'll never see these things. Between the time they wrote this thing and when they were actually developed, right? We went through World War II. There were great advances in nuclear technologies. We developed nuclear reactors, and so therefore we could make much, much more, basically sources of neutrinos which were inconceivable prior to the war. And as a result, the neutrinos were eventually detected, and so we knew of their existence. But just to give you an idea of the challenge, right? If we go to higher energies, like 1 GeV, 1 billion electron volts, which is typical of the neutrinos that we study, the cross-section is around 10 to the minus 38 centimeters squared. And that's you might get a sense that that's a small number. But to put that in context, if you just have matter, let's say some kind of normal matter, like water, something order gram per centimeter cube density that extends infinitely, and you shot a neutrino through it, it will typically go something like 10 to the 14 centimeters before it interacts. And alternatively, if you have 1 meter of material, then if you 1 out of 10 to the 12 neutrinos will interact. And so there's a big challenge in both producing neutrino sources, which are intense enough to give us enough neutrino interactions to make sense of what we're studying, as well as detectors which are large enough. And so that's basically comes down to a formula that looks like this, right? The number of neutrino interactions is given by the flux of neutrinos, the integrated flux of neutrinos that you produce, that cross-section that we talked about, and then basically the number of targets you have that are associated with that cross-section, right? And this is the size of the detector, the number, density, and this epsilon thing is just sort of a catch-all for your actual ability to detect a neutrino that interacts in your detector. And so the first challenge, as I mentioned, is to produce a flux of neutrinos which is as intense as possible. And so over the last few decades, there's been a very fruitful program of using high-energy proton accelerators to produce these neutrinos. And so there's this very cute cartoon here illustrating how that happens. We have a proton which comes in, impinges on some kind of target, could be usually beryllium or carbon. And then from there, we have mesons, which are produced as a result of the strong interactions. Now, the mesons, or in the pions, will typically come in three types: a positive one, a neutral one, and a negative one. The neutral ones actually basically don't produce neutrinos, but by using a magnetic device, we can actually focus one side of those neutrinos. And so we focus the positive ones and then decay them in this decay pipe. We get a beam which is primarily muon neutrino. Now, if we reverse the polarity of that device, then we focus the pi minuses, which then decay to produce muon antineutrinos. And so through this way, we can both produce a muon neutrino beam or a muon antineutrino beam, and basically set us up to study the difference between these oscillations and study the oscillations separately. So so these pions will enter this decay region, they decay to produce the neutrinos, and then we have what we call a beam absorber or stop that kills all the particles except the neutrinos, and the neutrinos will continue on to our experiment. So I put a little, I guess you can't see the buffalo, but you can see the CU, and just because, yeah, this device, I mean, it looks really cute here, abstract, but these are really real devices that are enormous, right? Typically, the extent of a device like this is hundreds of meters, approaching a kilometer. They operate under increasingly intense environments where we're sending almost a megawatt of a proton beam onto the target. So it's an extremely harsh radiation environment. In order to produce the magnetic fields that you need to do this bending, you have to send hundreds of kiloamps through an enormous magnetic device. And so, yeah, I think what's exciting here for Boulder is that you actually produce these things right here. And so I'm not going to talk more about it because the expert on that is sitting over there. Okay. The next thing is that, well, we can get more neutrino. So we can't really do anything about the cross-section, but we can do something about our detector. And so we see two factors here: the volume of the detector and the number of dense targets. And so in choosing what the detector looks like, well, the first good news is that the neutrinos will basically interact with any nuclear target. So you can make the detector in principle on anything. And so we typically look for something that's cheap, abundant, and manageable because we have to manage it in very large quantities. But the bad news is that we need to be able to actually detect a neutrino. It's not enough that the neutrino just interacts in your random material. We have to see basically the products of those neutrino interaction come out, so that we can say something about what that neutrino was, what its energies was, and what other properties they may have. And so within some kind of macroscopic bulk of material, we need to be able to detect activity on the order of GeV and lower. And to give you a sense, that's some kind of nanojoule of activity happening somewhere in your detector that you need to be able to detect. And in terms of this detection efficiency, right, as we spoke before, we need to be able to reconstruct what kind of neutrino it was by identifying its primary lepton, and do our best in terms of inferring its energy by measuring the energy of the particles which came out. Okay, so I'd like to talk about one particular technology, and so there's been a whole history of this, and one of this is called the liquid argon time projection chamber. And the basic principle here is that we have a huge volume of liquid argon, and liquid argon satisfies the things of being relatively cheap because it's common in the atmosphere. It's relatively dense, right? I think it's about 1.4 grams per centimeter cube or something like that. It's not so cryogenic that it's difficult to liquefy it. And it has a property, because of being a noble gas, that when you induce ionization within the liquid argon, it actually lasts for a very long time. And so when a neutrino comes in and sprays some charged particles in various directions, those charged particles will ionize the liquid argon. And the nice thing about the liquid argon is that electrons will remain detached for long enough that you can do a very interesting thing where you can put a large electric field across the detector volume, which then pushes the electrons to one side. And on the side of your volume, you can instrument and detect those electrons and effectively image the ionization which occurred inside the detector, and therefore the neutrino interaction. Okay? And so this turns out to be a very economic or efficient way of taking a large volume electric of a liquid argon and basically detecting ionization activity in it across many, many meters. And now we're talking about doing this on the scale of something like 10,000 cubic meters. So detectors which are almost 100 meters long, 10 meters high, 10 meters long. We just instrument, well, effectively one side of the detector, and that allows us to do imaging in this ionization on sort of the millimeter to centimeter scale. Okay? All right, so let's talk a little bit about, I'll come back to this technology. I wanted to talk a little bit about where our study of neutrino oscillations is right now. We got two experiments ongoing, TDK and NOVA, and they both have this feature of what we call a long baseline. We're sending these neutrinos many hundreds of kilometers from an accelerator site, in this case, the J-Park accelerator site, to the other side of Japan in Kamioka. In the NOVA case, from Fermilab outside of Chicago, almost to the Canadian border in Minnesota to the Ash River. And the reason why those things are so far away comes back to this proper time, we are looking at an oscillatory effect, and there is a proper time at which those neutrinos will reach the maximum oscillation probability. And so given the neutrino energies that we're producing, around 0.6 GeV here, sort of 2-ish GeV here, those neutrinos actually have to traverse about 300 kilometers in this case, 800 kilometers in this case, for that sort of aging process to sort of basically for this oscillation to ripen to its full glory. And so then you can sort of see the effect here that when we send these muon neutrinos from here to there, this is what we expect in the absence of oscillations, and this is what we actually observe. And so what's happening here is that we're producing these muon neutrinos initially, but as a result of the oscillation effect, they are turning into other neutrino flavors, electron neutrinos, tau neutrinos. And as a result, we see this enormous deficit of these muon neutrinos at the far site. And then if we map out sort of the probability relative to their initial production, we see this oscillatory pattern. And there's a similar situation here with NOVA, just at basically 3 times the energy and 3 times the distance. Okay? So we can look at the electron neutrinos as well. And since we have this sign-selected beam that we were just talking about, we can run both in muon neutrinos and antineutrinos. This is for TDK, muon neutrinos, muon antineutrinos, and look to see how often are we observing these electron neutrinos appearing in our detector at the far site. And so here, this is where disentangling all these things happen, right? If we see more electron neutrinos versus electron antineutrinos, that's indicative of a normal hierarchy and let's say a delta CP over minus pi over 2 favoring the neutrino oscillations over the antineutrino oscillations. If it were the other way around, then we would favor inverted hierarchy and plus pi over 2 in the phase. And what's interesting right now is that the TDK experiment does actually see indications that the nu mu to nu e process is happening more often than the nu mu bar to nu e bar process, which is sort of, if we sort of favoring this normal ordering delta CP equals minus pi over 2 phase. The NOVA situation is a bit different. They actually don't see that. And so I would say right now, if you take these two experiments together, the situation is rather indecisive. And so one thing that's about to happen is that these experiments are combining their results. And so hopefully we'll have a coherent picture of how, basically statistically and given the systematics of these experiments, how these come together and give the most definitive statement. But right now the picture is a little bit murky. Okay? And you can also get a sense of the statistics of the experiments, right? They're on the order of about 100 interactions across both experiments that we're dealing with. And so moving forward, we have two new generations of experiments that are coming about. The NOVA and TDK will continue to take data for at least the next few years. And then basically, we are planning two new generations of experiments which will have a leaping capability both in the statistics and the configuration. And so by statistics, I mean that we have more intense neutrino beams, so going from somewhat below a megawatt to above a megawatt, perhaps 2 megawatts of beam power, and also bigger detectors. So in the hypercompacted case, we're taking our existing detector and increasing it by nearly a factor of 10. We have the configuration of the experiment, basically how far the neutrinos go. In the the hyper-K case, as it turns out, this is the same as the TDK experiment. But in the Dune experiment, we're actually sending these neutrinos now not 300, not 800 kilometers, but 1,300 kilometers with a higher energy neutrino beam that will take it from Fermilab over to a underground facility in South Dakota. And the reason why we do this is to enhance that matter effect, which is dependent on this mass ordering. And so you can sort of see how these things differ, how dramatic this effect would be. That if the mass ordering was actually normal with the small splitting on the bottom, you would get this oscillation probability as a function energy. If it were on top, then you would suppress the neutrino mode, and then you would get this difference. And so that big difference, we hope, will give us a definitive statement about which ordering of mass states we have, and basically take that out of the picture so we can focus on some of the other parameters. And so, yeah, once again, the cartoons are kind of cute, and it leads to, it gives you a sense of what's involved. But these things are actually under construction. So this is one of the 4 detector caverns at Homestake, a mile underground in South Dakota, where I guess 2 of these liquid argon detectors will go. These are components of the cryostat to make that huge liquid argon volume that are coming in. These are the readout planes where we detect those ionization activity. This is a prototype of our near detector, I'll talk a little bit more about, which is going into a neutrino beamline at Fermilab. For the hyper-K experiment, we need to produce thousands of these photosensors. Likewise, they need a cavern and an access tunnel. So these things are happening, and with the idea that towards the end of this decade, these experiments will be in operation. So I like to switch gears. One of the things is that I wanted to give you a sense about is really the scale of these experiments, which obviously has its own technical issues. But I also wanted to talk a little bit about, as we progress, this is arguably the third or fourth generation of these experiments. And as we have more and more ambitious goals, obviously things get more difficult beyond just the technical issues of getting more statistics. And so I wanted to talk a little bit about, what's some of the new tricks up our sleeves we have in dealing with this. And to do that, I wanted to talk a little bit about how we actually measure the neutrino oscillations. I kind of glossed over it. But in essence, what we need to do is, at the far detector, right, we will observe some kind of spectrum of, let's say, electron neutrinos that arose from muon neutrinos turning into electron neutrinos. There'll be some backgrounds that we need to take out, so we need to understand those. But then basically the shape and number of these neutrinos, the shape of that spectrum, depend on the oscillation parameters. And so what we need to be able to do is actually predict for a given set of neutrino oscillation parameters, that is the mixing elements, this complex phase, the mass ordering, the mass splittings, what this thing is supposed to look like, right? And then basically we do a statistical analysis where we see which shape matches the best and then pull out what those parameters are supposed to be. And so what that effectively means is that we have to follow the neutrinos through this whole process. So they get produced in the beamline, and so there's some flux of muon neutrinos. As they go from the source to the detector, they do the physics that we're interested in, the neutrino oscillations. And then they interact, that's the cross-section, and then they produce particles which come out. And then there's a response to the detector to those things. And so basically, we have to convolve all these things in order to predict this spectrum. And that's sort of what's encapsulated in this formula here. That as a function of what we call the energy that we reconstruct, the number of neutrinos is given by this integral where we have the neutrinos that are produced, the flux of neutrinos that are produced, the oscillation probability, which is a function of the neutrino energy. There's a chance that it interacts and what particles come out, and then how the detector responds to that, and in particular things like the efficiency and the resolution for the reconstructed energy. Okay? And I think one important thing to note here is this integral over the true energy. Okay? And And the reason why this becomes important is that if we had very, very good energy resolution, right, then effectively, you would have some kind of delta function between this reconstructed energy and the true neutrino energy, and then the whole thing, the integral basically just collapses as a function of either the true or reconstructed energy. It doesn't matter. But as it turns out, that there's actually, the resolution effects are extremely difficult to, are first of all large, and very difficult to model. And so this integral turns out to be extremely non-trivial in its impact in interpreting these parts of the results. Okay, so some of the challenges are that, well, we need to understand all those elements of the neutrino, that process. And so we hit some problems already from the square one. That, well, how many neutrinos are we producing and what is their energy spectrum? Turns out to be an extremely complicated thing. And so there is we have the protons hitting the target and these pions come out. Well, how many pions came out? Well, what energies are there? We have this enormous sort of particle beamline thing, and it has the electromagnetics that steer the particles in one direction or another. And basically, modeling all that turns out to be a very difficult thing. And so difficult that I remember when I started in this field, people basically said it was impossible to predict this, that you can sort of model it and get a guess at it, but in a systematic way, you'll never be able to do this because there's just too many complicated things going on. I think things have advanced since, and so until recently, the state of the art was that we can sort of do this to roughly just better than 10% uncertainty. Okay? So that's one issue. Another issue is that the neutrinos interacting on a nuclei like argon turns out to be an extremely complicated process, which I would say to first order, we don't really understand. And so we do have these models that say, well, when how often the neutrino interacts, what particles come out. And so people have done studies like this, where, well, there's an analogous process by which we have electron scattering. And so we can put a target like carbon or argon into an electron beam and measure a particle, a quantity like the energy momentum transfer, which is relevant for what comes out of that interaction. And here is one of our state-of-the-art models. And here's the data, right? And yeah, in some cases, it seems to do OK. In other parts, yeah, I would say it would be generous to say that it doesn't do so well. And just to say, this reflects decades of effort, right? And it's one of those things where it's kind of a modeling whack-a-mole. You can sort of get certain things to agree, then other things don't agree. And then if you try to get those things to agree, then the things that you were doing before don't agree. And so that really points to the fact that we don't really understand the underlying modeling of this thing. And so we're somehow lacking some of the fundamental physics, and progress has been relatively slow on that front. I think another thing which is coupled to this is that, well, as long as you can get the energy, maybe you don't care. But the issue is that we have a real detector, and there are a number of complications which happen because we need to have a dense volume. So the neutrino interactions happen in dense volume. They have all sorts of secondary interaction effects within that dense volume. And as a result, as we try to identify what came out of this interaction, there are thresholds of whether we can actually detect a particle or not. Can we identify what kind of particle they are, and so on and so forth. And all those things go into that calorimetric information. And so to some extent, we are actually dependent on this modeling to be correct in order for us to correctly infer our energy resolution function. Okay? So that almost sounds like a mission impossible, right? That you basically need to predict, know all these things, but each one of them has some really fundamental uncertainties. And so one of the tricks that has been used for as long as we've been doing these experiments is actually to place a detector close to the source of the neutrinos before any of the oscillation effects come in. And therefore, we could basically study all three of these things prior to any oscillation effects. And so one thing that people have tried in the past is, well, we could try to measure the flux directly in a near detector by, you have the event rate, if you know the cross-section in your response, and you can infer what the flux is. But as we said, there's already uncertainty here and there. So that strategy kind of doesn't go very far, right? You basically can extract the flux to the level of uncertainties that you have here. And you can do any combination of these things, and you'll come up with the same issue. Another thing you can do is that if you have the same kind of detector in the near detector and the far detector, with the same kind of nucleus, the same kind of detection technology, this is what we call sort of the functionally identical detectors near and far. You can sort of look at this ratio, right? And then certain things we might be able to cancel out, right? Because the flux is in common, but there's this oscillation that happens. The cross sections are the same because they're the same target. The detectors are to first order the same, so these should be similar. And we try to cancel this as much as possible. But once again, we have this integral over the neutrino energy. And so to the extent we actually do need to have these things appropriately modeled as a function of neutrino energy for that integral to come out correctly. Okay, so that's another approach. There's another thing we can do is we can just throw the whole thing in there and say we're going to put in some nuisance parameters, like there's going to be some systematic uncertainties associated with the flux, with the cross section, and then also the detector modeling. And then we put the near detector together with the far detector. We have all these nuisance parameters. We try to constrain everything simultaneously. And in principle, that would work if we actually had the model and we believe those parameters actually represented the actual uncertainty that we have. But as I mentioned, particularly with the neutrino interaction modeling, that's not the case. And so likewise, this has some limitations as well. So that's the bad news. I'd like to turn quickly to the good news. So the first thing is that for a long time, the very large part of the uncertainty in the neutrinos was how often the proton, what happens when a proton interacts with the target and initiating the chain of producing your neutrinos. And so the good news here is that there's been experiments that actually measure these things, for example, on proton and carbon data. And so now we actually have a very good understanding of these things. And even so much so that we can hope that that part of the uncertainty will, by the time Dune comes around, is no longer the primary source of uncertainty for predicting the neutrino flux. And then we have other things like the focusing effects and the beam alignment and things like that. And so, yes, I put the buffalo here because I know what, this is just as a pretty picture of the experiment. Uh-oh. Right. I think that's the gap TPC, right, Eric? I'm not sure if the beam is going this way or that way, but that was the prettiest picture I found. So this is an experiment at CERN, which people here are very much a part of and really having a big impact on that first uncertainty about being able to predict the neutrino interaction, neutrino flux. We are also putting new capabilities into this near detector. And so in that cross-section modeling, how the neutrino interacts with an argon nucleus or whatever nucleus, well, one way we can get around that is if the neutrino actually interacts with something else. In this case, the atomic electron that come along with the nuclei. And so at that point, we can get rid of all this, what we call hadronic or nuclear uncertainties. And we have a process that theoretically we can predict to basically about 1% or more. And this is sort of like what we call a standard candle. And so by identifying this particular channel within our detector, in the near detector, we can basically do that strategy that we hope to do with something that has a very precise cross-section and measure the neutrino flux. And so the caveat here is that the cross-section for this thing is really, really, really small, something like order 10 to the 4 or 5, smaller than everything else. And so you have to have a detector that's capable of basically pulling this needle out of the haystack of all the other neutrino interactions. And so this is actually the first time, at least in Dune, that we will have a detector that's both big enough to have enough of these interactions and capable enough of pulling out this particular signal that we can actually use this standard, see this standard candle, and have sort of a in situ measurement of the neutrino flux. So that's the standard candle. We also have what I would call a variable candle approach. And there's an interesting thing that happens with the neutrino beam that since we're talking about trying to get as many neutrinos as possible, typically you would put your neutrino beam right on the axis of the beam because that's where it's most intense. And indeed that is the case, and that's sort of the neutrino flux at Dune you would get on axis. But as it turns out, if you move away from that axis, the neutrino beam starts to go to lower energy and becomes more peaked. And this is what we call the off-axis effect. And it is basically a feature of the two-body decay of the pions which are producing these muon neutrinos. And so we can actually, or what we're planning in Dune is actually have a detector that can move this distance, right? So you can see here, this is on axis. We go 5 meters away, 10 meters away, 15 meters away, 20 meters, 25 meters away. And basically, we have a neutrino beam that we can sort of tune to peak at different energies. And with that, by taking the data across all these different positions, we can verify that we actually have the energy dependence of all our modeling correct. Or we can even turn that around and use this dependence to try to, since we have some handle on the energy dependence of what we're observing, we can actually convolve that with the oscillation probability and predict directly what we expect to see in the far detector. And so this is what we call PRISM. And in the Dune near detector, it is actually implemented as a a movable detector system. We have our near detector here, a liquid argon time projection chamber, and a muon spectrometer that will move up to almost 30 meters off axis so that we can study the neutrinos at all these different locations. Okay? And yeah, I put the Boulder here because it is a former graduate student of Boulder, Mike Wilking, who has really been one of both the developers of this concept and its practical implementation in moving these kiloton detectors back and forth over 20 meters. This is also another interesting challenge. I think people, so the liquid argon TPC challenge is a very formidable one, but it's not perfect, right? Just like every other detector technology, it is a bunch of compromises. In particular, here we're just trying to get as big a detector as possible where we can get very precise imaging of the ionization, but with minimal readout channels. So the caveat here is that the detector is actually very, very slow because of this drift process. It takes something like milliseconds for these electrons. And that doesn't sound like a long time, but in particle detector technology, that's a very slow time. And meanwhile, the neutrino beam will send bursts of neutrino beams in the order of 10 microseconds. And at the near site, the neutrino beam is so intense that we kind of have the opposite problem that we were talking about, which is that we get something like 40 or 50 neutrino interactions happening at once in the detector. And given how slow this detector is, they effectively appear simultaneously. Okay? And so then the question is, we have to somehow pull all this apart. What belongs to which neutrino interaction? So if we want to know what the energy is, we have to make the right association between all the stuff that's happening in the detector and which neutrino interaction it belonged to. And so interesting, the solution to this was to sort of turn the whole concept upside down. On the one hand, the liquid argon TPC allows you to build these enormous detectors with minimal instrumentation. But the key thing here is that there's also an optical signal which is much faster than the charge signal, and which allows us to localize things on a nanosecond time scale. And so by actually chopping the detector up into small volumes, we can then localize what happens in a given detector with the optical signal that happens inside it. And basically gives us a way, with this nanosecond precision, to basically associate, based on what light gets produced by this, where it happens. And that nanosecond time resolution over 10 microseconds is typically enough to basically make unambiguous which interaction belongs to, or which activity belongs to which interaction. Okay? And so the challenge here is that we have this big volume of liquid argon, and we put all this stuff in it, right? All these walls to block the light. And so the challenge now is to make those structures as lightweight as possible. And so just last month, a couple of people from Boulder came over and tested this new concept for the electric field system that operated successfully. As you might imagine, for a complicated problem like this, one of the things that we are really pushing on are modern machine learning techniques, particularly visual recognition. And so we are getting to the point where we can take something like an electromagnetic shower, where there are all sorts of bits of information happening all over the place. Maybe there are multiple ones of those, and then we can use these algorithms to say which bits of information belong to which shower. And so this is sort of a graph neural network implementation. Likewise, this problem about if we have multiple neutrino interactions, which activity belongs to which neutrino interaction is also something that we are basically solving through these machine learning techniques. I wanted to mention, it's the last slide. So let me talk about this. So as I mentioned, the liquid argon TPC and any other detector technology is sort of a compromise of many things. And one of the things that's intrinsic in the compromise we made for the FAR detector is that we want to have a very dense medium, right? Liquid argon, so that we have enough mass, as many nuclear targets as possible to maximize the chance of a neutrino interaction. But at the near detector, because of the intensity of the beam, as you saw, we actually have the luxury of not having to do that. And so instead of liquid argon, why don't you use gaseous argon, where you will have much lower tracking thresholds, because the gas is much more rarefied relative to the liquid, though those particles will pass through the gas with minimal chance of secondary interactions. And then because we can magnetize such a volume and not be overcome by things like multiple scattering, we also get unambiguous sign identification. And so basically, this kind of detector where we have a gaseous argon detector using a similar time projection chamber technique, where we can image the ionization in a low density magnetized volume, could in fact be sort of the ultimate way for us to study neutrino-argon interactions. And so this is something that is basically a concept which we call ND-GAR. You sort of see a conceptual representation of this with a 0.5 Tesla magnetic field, a high-pressure gaseous TPC in there surrounded by electron calorimetry. People doing collider physics will probably think that looks similar, but the beam doesn't come this way. It actually comes, it goes that way. so what you call the end cap is actually, not along the direction of the beam. Okay, and yeah, so one nice thing was that you may have heard of this thing called the P5 report, which came out 2 months ago. And so this is basically, in some sense, a roadmap for a field in the US and what kind of major projects we should be supporting. And so they made some very strong statements about the need for this kind of detector in the future of Dune in order to further understand the neutrino-argon interactions at a level that will be commensurate with the statistical precision that experiment will have. Okay, so summary, neutrinos are, in some sense very simple particles, but they're also very perplexing. And they have an origin where, basically you were trying to solve some problems and their properties were just so, on the one hand, simply articulated, but so weird that we can barely justify their existence or that postulation. But despite that skepticism, the neutrinos are actually there and they're everywhere and have a really profound impact in understanding both the fundamental particles and interactions and why the universe is the way it is. The properties that we have, in particular their low cross sections, make them very challenging to study. But on the other hand, nonetheless, there's a huge payoff in understanding those properties because of the implications they have for this fundamental understanding. We still have a number of fundamental questions about these things, and some of them have to do with the neutrino properties themselves, but then also what those properties have to do with particular cosmology and certain extensions of particle physics beyond the standard model. And I always like to reflect that, like whenever I was entering this field 20 years ago, people keep saying that the neutrinos are entering the golden age of study, but it seems like the golden age just kind of keeps going on. So I think over the next decade, we have a lot of exciting things to do, and then maybe, hopefully, we'll uncover, we actually uncover all the tricks and mysteries of neutrinos so that we have a full understanding. Thank you very much.
Hey, thanks very much. Questions? Yes.
I have one question. I believe you've looked at least at some of the theoretical ideas that there's a fourth hyper flavor neutrino. How does it do in these experiments? Would they be useful detecting that, or is that something that's going to have to work its way out some other way?
Certainly having that, what we would typically call these sterile neutrinos that are more massive will definitely impact the phenomenology that we see here. I don't know that, so certainly within Dune, we will have some sensitivity to that. Right now, the experiment isn't really optimized towards specifically studying that. We may see some impact of it, but to really sort of have the data to interpret those things. And partly it has to do with the fact that, right, I talked a little bit about sort of this near-far setup, right? We look at the neutrinos before the oscillations, look at the neutrinos after they oscillate. And so all that has to be sort of now compressed. Now you're expecting the oscillations to happen on a kilometer scale, and then your detector has to come sooner, right? And so there are ways around that. If you have enough energy resolution, right, you may be able to see the oscillation and the pattern. And so experiments like Prospect using reactor neutrinos are doing things like that. I think that the experiment as it's currently configured, Dune, I think could use some improvement in that regard. But obviously, there's a detector hole there, and we can shove other stuff in there that can be optimized for that purpose. Yeah.
Yes.
Just to give me first a sanity check. If I understand, you said the difference between neutrino oscillations and anti-neutrino oscillations.
Yes.
Right?
In my opinion, yeah.
So intuitively, I would think that a detector that's built out of matter, there could be some complications in measuring the oscillations between neutrinos and
Yeah. No, there are definitely some complications, which come back to sort of some of the fundamental properties of the weak interaction, right? That neutrinos, quite apart from oscillations, neutrinos and antineutrinos will interact differently because of the chiral nature of the weak interaction. In particular, neutrinos have a much higher cross section. They tend to have more energy and momentum transfer, and so. Yes, so in that respect, there is a systematic that comes down to how well we understand that modeling, how well we understand basically we have to go through the whole thing, right? The neutrino flux versus the antineutrino flux, the neutrino interaction versus the antineutrino interaction, how the detector responds to each of those things, and so I think that is a complication. So far, I haven't seen a way in which that fundamentally limits what we can do, to the extent that, particularly in a near detector, we'll be able to study the antineutrinos in great detail, and really with enormous statistics understand some of the differences that we would be worried about. I mean, the alternative is you try to make a kiloton detector out of some kind of antimatter, and so.
Yes.
So you had an oscillation scheme, and you had the whole near detector. Apparently my voice has a low cross section. But so you mentioned Dune, and you had the near detector, far detector with the identical detector paradigm. And there was that problem with the near detector having so many interactions because of the neutrino beam current. Would you be able to sort of tackle this issue if you had multiple detectors in the beam path after the oscillation kicks in, and where, so right now it's just two, but if you had more, could you constrain that all your uncertainties in a slightly better manner?
I think in principle that is possible. This is where I would say we get into some real estate and geological issues, I guess, right? Just because the neutrino beam has to be pointed down, right, in order to basically point at South Dakota, and